Hello, today we're going to talk about higher order derivatives, so essentially derivatives of derivatives. So we're going to talk about some notation here. So we know the derivative notation is f prime. Well, if I wanted to take another derivative, so this is what we're going to call the first derivative. The notation for the next derivative, or the second derivative, is going to be 2 dashes. So this is the second derivative. F3 dashes is going to be the third derivative. And then rather than doing 4 dashes, we're going to start doing Roman numerals. So the fourth derivative is going to be that. Okay, and then this is going to continue. This would be considered the nth derivative. Okay, so why would we want to continue to take derivatives? Well, one good example, and those of you in physics already know this. If we have s of x, that's going to be position. And there's different notations that we can use for that, but I'm just going to use s. If I take the derivative of position, that gives me the rate of change of position, which is velocity. Okay, so if I take the second derivative of position, which is just the derivative of velocity, so the rate of change of the velocity is acceleration. So these are pretty commonly used, so position, velocity, acceleration. We just keep taking derivatives to get there. You can even go one more. Okay, the third derivative, and sorry, this should be a there. The third derivative would be the second derivative of velocity, which would be the first derivative of acceleration, is called jerk. And then if you do it again, the next three are snap, crackle, and pop. An alternative notation for the derivative is dy dx, because again, it's the change in x over the change in y. So using this notation, the derivative of that is going to be d2y over dx2, because you're taking the second derivative of y with respect to x. And then if we do the third derivative, so if I take this is going to be d3 over dx3. For the most part, you just need to recognize this notation as this is the second derivative and this is the third derivative. All right, so let's do some derivatives. So we have the function y equals 4x to the fourth plus 2x cubed plus 3. And we're going to just keep taking derivatives. So the first derivative is going to be 16x cubed plus 6x squared plus 0. Next derivative, we'll multiply 3 and 16 to get 48. 6 times 2 is 12. Next derivative, 48 times 2 is 96x plus 12. Then we're going to have 96, and then we're going to have 0. And all polynomials will eventually go to 0 if you take enough derivatives. So our observations are, how many derivatives did it have to take? Well, we had a degree 4, and we had to take 5 derivatives, and that pattern will follow. So polynomial of degree n takes n plus 1 derivatives to equal 0. All right, so we have this function, and we're going to take the second derivative. So we're going to first find the first derivative, df dx. So this is a quotient, so we need to use the quotient rule. So it's going to be the derivative of the top times the bottom minus the derivative of the top, or bottom times the top, all over the bottom squared. So the derivative of x plus 1 is just 1 times 2x minus this derivative is 2 times x plus 1 all over 4x squared. Now typically I'd say just leave it here, but since we're going to have to do more with this, it is advantageous to simplify. So this is going to be 2x minus 2x minus 2 over 4x squared. So 2x minus 2x goes away. So we have negative 2 over 4x squared. The 2's cancel. So this is going to be negative 1 over 2x squared. And I'm going to have to take this derivative again. So I'm going to write this as negative 2x to the negative 2. So we're taking the derivative of this, and you could also use the reciprocal rule, but I'm just going to go ahead and do this. So my second derivative negative 2 times negative 2 is positive 4x to the negative 3. Okay, scratch that. Go back here. I did a bad thing. 1/2 is still 1/2. So this is going to be 1/2 x to the negative 2. So d2f over dx2. We're going to have a negative 2 times a negative 1/2, which is going to be a positive 1. And then we're going to have x to the negative 3, or we could write this as 1 over x cubed. Now I did this one using the power rule. In the notes, I used the reciprocal rule and arrived at the same thing, if you want to take a look. Okay, this next one, we want to find the third derivative. Now, at first glance, you might be tempted to use the product rule, and you can, but we're going to have to take this derivative twice. Or 3 times. So I'm going to simplify this by FOILing. So y 5x squared times 7x cubed is going to be 35x to the 5th. We're going to have a 5x squared times an x, which will be a 5x cubed minus 21x cubed minus 3x. Again, you don't always have to simplify, but if you're going to be doing stuff with it, it is helpful to simplify. So I'll combine those like terms. Now I'll take the derivative until we get to the third derivative. So y prime, 5 times 35 is 175. This will be x to the 4th. 16 times 3 is 48, x squared minus 3. Our second derivative, 175 times 4 is 700 x cubed. 48 times 2 is 96x. That goes away. our third derivative. 700 times 3 is 2100x squared minus 96. So here it's easiest to simplify. Now, if you went through and did the product rule, you'll eventually arrive at the same thing if you simplify, but looking at things to make your life easier from the beginning is a good thing. Here we're going to find the fourth derivative of ax to the fourth plus 2bx plus c. So y prime is going to be 4a x cubed plus 2b x, and then the c is going to go away. Our second derivative, 3 times 4a is 12a x squared plus 2b. Our third derivative is going to be 2 times 12, which is 24a x. That's a constant, so that's gone, which leaves our fourth derivative is 24a. All right, so this one, we're going to find the 50th derivative, which you can knock yourself out and do all 50 derivatives, but we're going to look at the pattern here. So if f of x is cosine, f prime of x, the derivative of cosine, is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is positive sine. And the derivative of that goes back to cosine of x. So this is going to repeat. So every fourth derivative is going to be cosine. So 8 will be cosine, 12 will be cosine, so we just need to figure out where 50 fits into that. So if I take 50 and divide that by 4, we get the biggest number that can be divisible by 4 evenly, that's less than this, would be 48. So 48 divided by 4 is 12, and that leaves a remainder of 2. Who thought you'd use remainders anymore? But the 48th derivative would be cosine. The 49th derivative would be negative sine. The 50th derivative is going to be negative cosine. So all of these are going to be the divisible by 4, and then you just figure out what's left over. So this derivative is a negative cosine of x. Okay, we want the nth derivative. So we're going to come up with a general equation for what's happening to this derivative. So we know, and it may be helpful to treat this as x to the negative 1 if you want to. So f of x is 1 over x. The first derivative, and this is one you should know, is going to be negative 1 over x squared. And it comes from the fact that since this is in a separate color, is x to the negative 1, if I bring down the negative 1, we get negative x to the negative 2, which turns into this. So if I do this derivative, we're going to have our second derivative. I'll fill in that in a second. This is going to become positive 2x to the negative 3, which is a positive 2 over x cubed. If I take that derivative, this is going to be a negative 6x to the negative 4, or negative 6 over x to the 4th. I'm going to do one more. Okay, I'll do this one first again. So 4 times negative 6 is 24 x to the negative 5. All right, so there's three things that we're essentially dealing with. The first is the numerator, so 1, 2, 6, 24. And 1, 2, 6, 24, so here we're multiplying by 2. 2 times 3 is 6. 6 times 4 is 24, so we're multiplying by the next number. If you remember in pre-calculus, those are factorials. So the numerator is n factorial. Okay, if I want the fourth derivative, that numerator is 4 factorial, which is 24. Then we have the exponent. Okay, when we took the first derivative, it was 2, second derivative was 3, third derivative was 4. So the power is going to be x to the n plus 1. It's one bigger than the derivative we're trying to take. And then it's alternating. So a way to make it alternating is take -1 to a power. So when it's odd, it's negative. When it's even, it's positive. So if I make this -1 to the n, any odd number I plug in there is going to make this negative. Any even number is going to make this positive. This next example show that y equals 1 over x satisfies x cubed y, second derivative of y plus x squared y prime minus xy equals 0. This is what is called a differential equation. You don't have to worry about that much right now, but that's what it's called. So I already found these derivatives, so I'm not going to try them again. We'll just use the ones from above. So the x's will stay x's. We're just going to replace the derivatives with what they are in terms of x. So this is going to be x cubed. The second derivative is 2 over x cubed plus x squared y prime is a -1 over x squared minus x, y is 1 over x. And we're hopefully going to see that this is 0. So we'll simplify this down. X cubed times 2 over x cubed, those cancel, so we're just left with 2 there. Here, x squared times -1 over x squared is going to be -1. Same thing here, -1. And 2 minus 1 is 0, which means that satisfies that differential equation. Eventually in Calculus BC, we're going to get to something called series, and we dealt with series in pre-calculus. Now we're going to look at series and take their derivatives. So this one you actually saw in pre-calc. If you think about this as an infinite geometric series, we're multiplying by x. The sum of an infinite geometric series is a1 over 1 minus r, and we saw that. So if you remember that, fantastic. If you don't, that's okay. We can still find the derivative. So this equals this from infinite geometric series. So the derivative of this is going to equal the derivative of this power function. So derivative of 1 is 0. Derivative of x is 1. X squared is 2x. 3x squared plus 4x cubed, and so on. Nx to the n minus 1. The second derivative, the derivative of 1 is 0, 2 is 2, plus 6x, plus 12x squared, and so on. So this would be n minus 1 times nx to the n minus 2. Again, eventually, we're going to discover that cosine of x can be written as an infinite series, and this is the infinite series representing cosine. So if I take this derivative of 1 is 0. This derivative, I'm going to have -2x over 2 factorial. This will be 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial. This we multiply down, so we'd have 2n times negative 1 to the n x to the 2n minus 1. Okay, and then I can simplify these, and I will just for the sake of comparison. So this is going to be negative x over, so 2 over 2 is just 1, so x over 1. The 4's are going to cancel here. So this is going to be 4. If I divide a 4 out of 4 factorial, I have 3 factorial. And then if I divide a 6 out of 6 factorial, we're left with 5 factorial. And here the same thing with the 2n's. So this is going to cancel 1 2n with 1 2n. So this is going to be negative 1 to the n, x to the 2n minus 1, all over the number 1 less than 2n minus 1, or 2n, which is going to be 2n minus 1 factorial. So the derivative of cosine is this. And here's what sine is equal to. If you notice, this and this are opposites, which match. If I take the derivative of cosine, I get negative sine, so that's opposite. Don't worry about where these series are coming from. We're just looking at some connections here. So we can do the same thing with sine. So we're going to have 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. Here we're going to have 2n plus 1, negative 1 to the n, x to the 2n plus 1 minus 1 would be just 2n. And then simplify it again. So 1 minus 3 factorial divided by 3 is just 2 factorial. X to the 4th over 4 factorial minus x to the 6th over 6 factorial. The general equation, the 2n plus 1 and 2n plus 1 cancel. Which means we want the number 1 less, which is 2n. And if you notice, this is exactly the same as cosine, which is the derivative of sine. Okay, back to something that's maybe a little bit easier to wrap your head around. Let f of x equal the absolute value of x plus 1. So which of the following statements are true? Well, x plus 1 is going to be shifted to the left 1. So is this continuous at negative 1? Yes. Is it differentiable? No, because it has a corner. So 1 and 3 are our correct answers, so that's going to be D. Now I actually want you to take out your homework for this section because I'm going to work through the front of this with you. So this is the higher order derivatives. Okay. So these first 3 are all definition of derivative. This one is the one we are most used to. This is f prime of x. We can also call this a right-hand derivative. This is the one you're going to see most commonly representing when we ask for the definition of derivative. That's what we're looking at. This is this, but backwards. So it's still f prime of x, but coming from the left-hand side. This one's pretty rare. This is still f prime, but it's a symmetric definition, but we typically won't see that, but just in case you do. now we move into actual numbers. So this is the same as this. Instead of x though, we have 2. So this is f prime of 2. This is our alternate definition. This would be f prime of 4. So this is the limit as x approaches a of f of x minus f of a over x minus a. This is just evaluated at 4. Okay, this next one, notice we have x plus h squared minus x squared. So back to the definition of derivative. Okay, rather than having a generic f that we're evaluating x plus h and x in, we have an actual function. So this is equal to the derivative of x squared. The function in this case is x squared. So this is the derivative of x squared, which is 2x. This looks just like this, except for instead of x, we have 3. So this is the same as saying x squared, take that derivative, and then evaluate it at 3. So that's going to be 2x evaluated at 3, which is going to be 2 times 3, which is 6. This one, our function that we're taking the derivative of is sine of x. We're evaluating that when x is pi. So you don't have to do the limit derivative. We're just saying that this is another way of saying this. So the derivative of sine is cosine. And we're going to evaluate that at pi. So that's going to be the cosine of pi. So that's the x value at pi on our unit circle, which is -1. Okay, these two here replace the h with a change in x, but it's the same thing. So here we're looking at the function, and I kind of always look at this last one because it's a little bit easier to detect, but this is going to be 5x to the 4th. We're taking the derivative and we're evaluating it at 2. So this is going to be 20x cubed evaluated at x equals 2. So that's going to be 20 times 2 cubed, so 20 times 8 is 160. This last one here, the x is not a number, so this one's just the generic derivative, not evaluated at a specific spot. So this is just cosine of x squared, that derivative. So the inside here is the x squared. So we're going to have the derivative of cosine, which is negative sine x squared, times the derivative of the inside, which is 2x.